Okay, welcome to 2017 question C3. Okay, we have surface geometry. Right, so we have the recycling bin, two trapeziums, okay, that we can see sloping. And we've got three transition pieces. Alright, okay, they're in the middle and then two on either side. Okay, we have to draw the given plan elevation of the 5 surfaces of the transition piece. So the scale is 1:6. Okay, here are the dimensions given, so we have to divide each dimension by 6. We'll eventually have to get the dihedral angle, true lengths and developments, and draw in the openings. Right, so I'll sketch out just the outline of it before I start technically drawing the question. So I have the dimensions marked out. Okay, so here's what it's looking like. Right. We'll be able to draw that technically in a moment. Here's our XY line. Okay, that's surface C complete. Surface A here now, marked in. That's surface A. This is surface B I'm doing. So that's the elevation complete. And then in plan view of two rectangular surfaces, left and right. And same here. And then surface A is in here. Okay, connect them together like that. So that's A, and then surface C. So that's surface C. Oh, sorry. Just got that line wrong there on C. It's meant to connect here. So that's surface C, and then surface B over here. So dimensions, that's 30, okay, 60, 15, 20, 15, 60. This one is 10, 10, okay, and then 240 divided by 6 is 40. Okay, 240 divided by 6 is 40. Okay, so I'm going to draw that out technically now. And actually, just before I start, I'll show you the model in 3D. Just hide that line. So that's what it looks like in 3D. Elevation, plan, and then the projections, okay, onto the relevant planes. Right, so we get going. So it's 60, 15, 20, 15, and 60. Okay, height is 30. It's going to heavy that in one go. Surface A. That's surface A. This is surface C. surface B there. Right, so plan view. So I can drop down whatever distance I want to start my plan. So I'm going 10, and then there's the markings are 10, 10 and 40. Where did I get that from? Well, here are the dimensions: 60, 62, 40. Remember, the scale is 1:6. So here's surface A, surface C, okay, so there's A, B, C, there's the plan view done. The next part of the question, okay, is to find the dihedral angle between surfaces A and B. So what does that mean? It's the angle of intersection between the red surface here, okay, and the orange surface. So we'll get them up now. Okay, so it's the angle of intersection between them. So here's one surface, the surface A, or surface B rather, projecting as an edge, and there's surface A projecting as an edge. So it is the angle between them. Okay, so the angle between them. Alright, and in order to see the angle between them, you need to see your line of intersection as a point. Okay, and the only way you can do that is to look along the true length of the line. So you have to look along the line of intersection's true length. And this is our line of intersection here, and that is not a true length at the moment because it's not parallel to the XY line. So I'm going to just sketch this out before I draw it technically. Okay, so I'm about to get cracking at this. So I need to establish my line of intersection. Here it is, line 1, 2. I'm going to label the points here: 3, 4, 3, 4, 5, 6. There we go. So up here is point 5. There's point 1. Here's point 6. Now you got to look along the line's true length. Okay. Now I have to ask myself, do I have the true length of this line already? The answer, okay, here are the scenarios where a line is a true length. Okay, if it's parallel to the XY line in elevation, it's a true length in plan. Okay, is the line of intersection parallel to the XY line elevation? No. If it's parallel to the XY line in plan, it's a true length in elevation. Do I have the line 1, 2, the line of intersection parallel to the XY line in plan? No. Or if it projects as a point in one view, it's a true length in the opposite view. Is that happening for me? No. So if I want to get the true length, I'm going to have to look perpendicular to that line. So I'm going to look perpendicular to line 1, 2 to get its true length. So I'm going to look perpendicular to that. So I'm taking an auxiliary elevation. I'm also going to project points 5 and 6. So I'm doing an auxiliary here. Here's my x1, y1 line. It's an edge of my horizontal plane. I'm going to take my height from elevation. So I'm going to take the height of 1 and 2 from elevation. Okay, or here's point number 1. So there's point number 1 from my auxiliary. Point number 2 is on the XY line elevation, so it's on the XY line here. So there's point number 2. Here's point number 1. And point 5 is the same height as 1. So there we go, there's 5, and 6 is on the XY line. And here's surface B. Surface A projects as an edge there. Surface A. Now, I'll just do that now. So we'll do the auxiliary, and then I'll show you the next step in doing find the dihedral angle. Will then be look along the true length of the line 1, 2, the line of intersection. So I'm projecting off my plan view. X1, Y1 line perpendicular to my projection lines. Heights taken from elevation. I'll label these points as well. 1, 2, 5, 6, 5, 6. So the height of 1, okay, I know is 30. So you can use your compass or just mark in 30. Okay, same as the height of 5 is 30 as well. Okay, and number 6 is on the XY line. I think I might have marked, I think I marked those points there 5. I actually marked it, it's 5 centimeters because I was talking about number 5, and you know the way mark 5, then you know the way if you're talking about something, you sometimes write it down. If you're writing someone a text, you get distracted. Okay, so here's surface B. So there's B. Surface A is an edge. There's 2, 1, 5, 6, and then 3 and 4, also slash 4 slash 3. So surface A projects as an edge because line 1, 3 projects as a point. Now I'm going to follow on with my sketch here. So this is the true length of the line of intersection. So TL of LOI. And what I'm going to do next now is I'm going to look along that line of intersection. So I'm going to project parallel to that line of intersection. So I'm taking the second auxiliary. And I'm going to draw in my X2, Y2 line. Okay, perpendicular to that. So there's my X2, Y2 line. And I'm going to take the distances from my X1, Y1 line back. Now because there's not a lot of space, what you can do is add in a datum line if you want. So I can take the datum here, and I can take the distances from my datum line back. So here's 4 and 3. So there's 4 slash 3. So line 4, 3 projects as a point. Okay, now I can take the distance for line 1 and 2. So from my datum line back, line 1 to 2 is going to project as a point. So there's 2 slash 1. Okay, and then the next one. Okay, line 5 and 6. So from my datum line back to 5, okay, is here. So that's point 5. So there's surface A projecting as an edge, and then number 6. Okay, is up here. I can join them together. Okay, so surface B now is projecting as an edge. So that's surface A as an edge view. Here's surface B as an edge view, and the dihedral angle is the angle in there between them. I'll just quickly show it to you in 3D. So there's the angle there from looking along the true length of the line of intersection. And here's the concept in 2D. You find the line of intersection as the true length and then look along it. Okay, so I'll draw that technically now. So my set square lined up. Project along the line of intersection. Can mark in my x2, y2 line. Remember, I could take my distances from my x1 and y1 line back. That takes a lot of room. So I'm just going to use a datum line. So here's my datum line here. Okay. So I'm going to go datum line back to 4 and 3 and mark here. So line 4 to 3 projects as a point. So once the line projects as a point, the surface it rests on projects as an edge. Line 1 to 2 is going to project as a point, so I'll follow 1 there, and 2, that projects as a point. So because line 1, 2 is on both surfaces, once line 1, 2, the line of intersection, projects as a point, both surfaces are going to project as edges. So datum line back to 5. That's all you need really. You could skip 6 if you wanted to. So datum line back there. Mark it up. It's kind of run out of my page there. So I'll put it in now in a second. So that was point number 6 up there. Point number 5. Okay, here's the dihedral angle. Here's surface A as an edge view. Okay, here's surface B. And it's a good idea always get your protractor in the exam, measure the angle and write down the value of the angle, or you could lose marks. So I'm getting 159 degrees. Okay, so that's part B done. Right, so we're on to part, I think it's part C now. Okay, part C. We have to determine the true length of the shortest diagonal on surface C, and hence using triangulation. Otherwise, draw the given one-piece development of the transition piece as shown in figure C. So we got to draw this development, and we got to draw a line. It's the shortest diagonal across surface C. So what does that mean? Okay, right. So here's a diagonal joining 2 corners in 3D, and here's another one. Okay, one is clearly longer than the other. So we have to find, okay, we have to draw that in, and then we have to find its true length. Okay, and draw true length. Okay, so we can find true length by using a rotation or an auxiliary. So I can rotate the line until it's parallel to the vertical plane. So this line here that I've rotated is parallel to the vertical plane. And once I rotate that, it's the true length in elevation. So here's the concept here. Okay, and that's the true length of the short diagonal up there. So I'm going to do that on my sketch, and then I'm going to draw technically this so I can find where I put my sketch. Okay, which at the moment I can't. Okay, so as I was doing earlier on, I was going through the scenarios of the true length of a line. If it's parallel to the XY line in the plan, it's the true length in elevation. So we're going to do similar here with our short diagonal. So 3, 4, 7, 8. Now, here's 7 in elevation. Here's the shortest diagonal in elevation. Now I'm going to rotate line 4 to 7, okay, until it's parallel to the XY line in plan. I'm going to rotate the line until it's parallel to the XY line in plan. Now, I'm going to bring that point up. It doesn't change height. Here's the new 4, and I'm going to join 4 to 7, and that's the true length of the shortest diagonal, 4 to 7. So I'm going to do that. Now, I'm going to rotate this line until it's parallel to the XY line. Bring that up, and here's the true length of the shortest diagonal there. Now, next part of the question says using triangulation, otherwise develop the whole surfaces, right? So here we go in 3D what that means. So this means we put everything onto the horizontal plane, all the surfaces. Okay, the triangulation, okay, is dividing the surface into triangles. So I'll show you that now. So this, okay, triangle inside these 3 lines, okay, this one here is the true shape of that triangle there. From this edge bounded by the shortest diagonal and the adjacent edge there. Okay, so we're going to divide this into triangles, and every line on the development is a true length. So I'll go out and I'll do it in the sketch. Okay. So surface C. Okay, you can draw a line across the bottom of my page, and in a development you have to be able to recognize true lengths. Line 4 to 8 is a true length because it's on the XY line elevation. So I can take the distance of 4 to 8, okay, and put it onto this horizontal line I've marked in. Okay, now if I get 0.7, I have a third point on the surface. So I'm going to take the true length of 4 to 7. I'm going to take the true length of 4 to 7, and I'm going to swing that from number 4. So I'll take the true length of 4 to 7 and swing from number 4. Now somewhere along this arc lies number 7, but we don't know where exactly along that arc lies number 7. Now line 8 to 7 is a true length in elevation because 7 to 8 is parallel to the XY line in plan. So if I take my compasses and set it to the true length of 8 to 7 and swing an arc from 8, now I have point number 8 exactly on this development because, okay, that's the true length, right? I want to establish now point number 3. Line 3 to 7 is a true length in plan because it's parallel to the XY line, okay, it's parallel to the XY line elevation. So if I get my compass, set it to 7 to 3, and swing from, okay, number 7, sorry I call that point 8. So I swing from 7, it's going to be somewhere along this arc. Now where exactly is it going to be? Okay, point 3, where exactly is it going to be? Well, if I get the true length of 4 to 3, okay, from my auxiliary, and swing it from number 4, it's going to be, okay, up there. And line should be horizontal in our development, okay, because parallel lines are parallel in every orthographic view. So that's 3, okay. And then the rest of it there, right? So surface A, okay, I can go perpendicular to that line as the true shape of surface A, okay, is going to make a right angle to line. It'll have right angles in here. So I can take the true length of line 3 to, what am I looking for here? I'm looking for the distance, okay. The true length of 4 to 2 in plan, okay, 4 to 2 in plan is the true length, okay, because it's parallel to the XY line in elevation and vice versa. So there we go. That's the true shape of surface A. That's C. And we can go this side as well. Right angle here. Mark 10 along it. There we go. Now, then we want to get surface B, which is a little harder, right? So we have point 2 in it. We have point 1. Okay, we need to get points 5 and 6, right? So I'm going to take 2 to 6 from plan, because 2 to 6 is a true length in plan because it's on the XY line elevation. And I'm going to swing an arc there. Somewhere along that arc lies point 6. Now how do I know where exactly it is? Okay, so I could find the true length of the longest diagonal, or I can repeat what I've done here. 5 to 2 is the same as, okay, 4 to 7, right? So there's 2 to 5. Okay, there's 2 to 5 there. It's the same as this one here. To find 0.5, I can take this distance here in plan, 1 to 5 because it's a true length, swing from number 1. Then I can take the true length of 4 to 7, which is the same as 2 to 5, and I can swing from 2. And where they intersect now is point number 5. Okay, and I can join that there. And then I can take the true length of 5 to 6 in elevation, because 5 to 6 is parallel to the XY line in plan. And I can swing an arc from number 5. Okay, where they intersect, that's point 6. Okay, now the sketch is a bit off, but they should be parallel. 5 to 1 and 6 to 2. Sorry, they might necessarily be parallel. I'd have to check them in my drawing. So recap there on an earlier thing I said about this being horizontal. It may not be. I'll have to check now in a few moments. So apologies on that error of speech. And then little surface up there, 10 right angle. We can mark it in. Right. So I'm going to draw that technically now. I'm at 28 minutes. The question said it was a trapezium, so they should be parallel. Okay, there we go there. Okay, so I'm going to do surface C now. Okay, take the length of 4 to 8. So I can mark it anywhere I want along that line. That's 4. Now I need to get 7. So I'm going to take the true length of 4 to 7. I'm going to swing an arc there. So somewhere along there is point number 7. I'm going to take the true length of 7 to 8 from elevation because it's parallel to the XY line in plan, and I'm going to swing there, and that's point number 7. So that's point number 7. Now I want to get point number 3. So I can take the true length of 7 to 3 from plan, swing an arc from there, and the line should be parallel to 4 to 8 because parallel lines are parallel in every orthographic view. So that's number 3. I've a dashed line here representing the fold line, and I should have put something else in there. I should have put that in as a dashed line, my bad. Okay, then I'm going to do this here. So this little flap, there are 10. Mark 10 on that. Okay, now I can do surface A now. So I can, to get point number 1 on surface A, I can take the line 1 to 3, which is a true length, because it's parallel to the XY line in elevation, so it's a true length in plan, and it's a true length in elevation. And the distance is 20. It said on the question it was 120 to scale, so it's 20 in a draw. Now I can draw a line, okay, parallel to 3, 4, because line 3, 4 is parallel to 1, 2 in plan and elevation. So parallel lines are parallel in every orthographic view. Okay, so that's, we have, okay, number 1 there, okay, and number 2 down here. Now to find point number 5, as I was saying, I can take line 2 to 5 is the same as line 4 to 7. Okay, so I can take the true length of 4 to 7, okay, and I can swing from number 2. And swing from number 2, and then I can take the true length of 1 to 5 in plan, because it's parallel to the XY line elevation, that's why it's the true length, and swing there until they intersect. So that is point number 5. Now I can then draw a line parallel to 5 to number 1, from number 2, and I can take just the true length of 2 to 6 in plan and put that from number 2, and this will be where number 6 is, dash line. So that's number 6, and then I've got a little flap to draw 10 millimeters. So I can mark 10 along that. Now, the last thing you have to do is the opening on each face, right? So it says the openings are 10 millimeters offset. Now I'm running a bit tight on time, so I'm just going to draw this in technically. So it says the openings are 10 millimeters offset, and draw them in plan and elevation. So if you want to do that, we essentially got to put the 10 offset into our development and transfer onto here. We've got to put them on our development and transfer to here. Right, so I'm going to mark in 10 in my plan from each one, so sliding set squares. And then on the opposite side here I'll do it. And I'll go up and down 10. Now every line on a development is a true length. So if we can get the distances on our development, we can transfer them onto our openings. Okay, right. So 4 to 3. Okay, 4 to 8 rather is a true length. That's a true length in plan. Or in our, sorry, I didn't second put that up on the camera. Sorry about that. I was drawing through them there. I just offset it by 10. So sorry there. I didn't have this up on the camera, so I just lined up my set squares, offset 10, drew in the lines. Now this is the true length here. Okay, so I'm going to take this true length and plot it on the true length here, 4 to 8. And likewise, I'm going to take this here. I'm going to take my compass right there and plot it on the true length 4 to 8. The parallel lines are parallel in every orthographic view. Now, I'm going to draw a line parallel to 3 to 4. So I'm going to draw a line parallel to 3 to 4 and 7 to 8. And then I've got to draw these distances up as well. So I'm going to take this line, that's 7. So I'm going to take this line here, okay, and I can put it onto the true length here, okay, in our auxiliary, and then I can bring it back until it hits line 3 to 4. Okay, and then I'm going to draw a line parallel to 4 to 8, because parallel lines are parallel in every orthographic view. So here's 2 points on the opening, okay, that I can heavy in. So I can heavy them in. Now I'm going to do the same here, right? So I can take the true length of 7 to 8 there, and I can put it up here, and I'm going to go parallel to line 7 to 3 in elevation, and I can drop that down to plan. Okay, and then I can go parallel to line 7 to 8 from plan, or 7 to 3 from plan rather. So this one there. Okay, and there I have one line done. I have that one done, that one done, I have this one done, and then I just need to get this one here. So I can take this true length here, I can plot it here, and then I can bring it back to my plan view. Okay, and I can bring that back. I kind of felt like I had done something wrong with my development there, so hard, which I do see. It was like this line here wasn't right, and I can't really remember what I done for it. I swore I took this distance and put it up there, which to be honest should have worked, but maybe it was just a bit inaccurate. So I can heavy in the line now. And then the other side, okay, I don't know, to be honest, for speed, I'd mirror the points across for speed. That's what I do. Okay, so you got your center line. And I think we have to draw them in elevation as well. So just take this point, plot it over. Okay, parallel to line 1, 2. For accuracy, make sure it's parallel to line 2, 6 rather. Don't know why I said 1, 2 there. We know then we're going straight up. It's like a translate, or with axial symmetry. Okay, flip this one over here. There's my plan view done. Then I have to do it in elevation. So I can bring these two lines up until they hit 5, 6. Okay, then bring them until they hit 5, 6 in elevation. Parallel lines are parallel in every orthographic view. So I'm going to bring them across and over to here. So you can see that bit of inaccuracy. However I managed to do that earlier, I don't know, but they should be all, there shouldn't be that gap there. I can bring this up to here then. Okay, to there. Can connect them together. There we go then. That's the question complete. Okay, probably video is far too long. I won't do the sketching in the future. I'll just show you the finished sketch rather than sketch out what to do. Is that just took too long? Right. Cheers, thank you, bye bye.